Okay, so let's get started with a quick recap from what we talked about last time. First off, we talked about functions. What's a function?
It's a set of ordered pairs that...
It's a relation or a set of ordered pairs such that with a special property.
Right.
Not every relation is a function. How do you check if a relation is a function? What do you check for?
You check if the domain, if the range varies for one domain, I think.
You check if every input has a unique output.
Yeah.
Right?
Yep.
That's what you check. So what do you check? If your inputs are equal, then your outputs better be equal. That's how you know it's a function. If the same input always gives you the same output. Make sense?
Yep.
Now we talked about properties a function can have. One of the properties we talked about a function having is a function being one-to-one. What did it mean for a function to be one-to-one?
Its inverse had a unique output.
Its inverse was also a function, is one way that we said it. Or the other way that we said it is if the outputs are equal, then they came from the same input. Equal outputs implies equal inputs. Then it's a one-to-one function. Make sense?
Yeah.
Cool. Now, we have this special notation. F colon A arrow B. How do we read this?
Function from A to B.
F is a function from A to B. What does that mean when we say F is a function from A to B?
A has the domain, B has the range.
Almost. So F maps every element in A to some element in B. So the domain of F is going to be A, but the range or image of F is just a subset of B. Maybe all of B, maybe not. But for sure a subset of B. That make sense?
Yeah.
Now we had a special property calling a function on 2. If the image was all of B, then we called the function on 2. Right? And then finally, what was a bijection?
1 to 1 and on 2.
A function that's both 1-to-1 and on 2. Then we call it bijection. It maps everything in A to everything in B, and it maps it so that every element in A goes to one and only one element in B, and every element in B comes from one and only one element in A. A bijection. We also think about a bijection as like a pairing off of all the elements. Okay, so that's a quick recap from last time. Now today, we're going to be talking about permutations. Now, permutations are something that we're going to come across in this class, and then we're not really going to see them again. We might use them just as an example of a group when we get to abstract algebra. So they may come up one or two more times as examples of things, but for the most part, won't really see them again. So why do we cover permutations? The reason I'm covering permutations is, one, I want you very comfortable with functions. So if you can get, a permutation is going to be a special type of function. Okay? A relation was a special type of set, a function was a special type of relation. Now a permutation is a special type of function. That's what permutation is. So the reason we're doing permutations is get you really comfortable with functions, hopefully, and then get you really comfortable with function composition. Now we remember what function composition was. Intuitively, what's function composition?
It maps from one function to the other.
It's like combining two functions in one go. Right? So if I had, this is a set A, this is a set B, this is a set C, I might have a function f, which maps the elements of A to B, and I might have a function g, which maps the elements of B to C. Then g composed with f, remember you do the right-hand function first, g composed with f maps the elements from A to C. It's like doing both these functions in one go. Remember this? Remember function composition? No? You watched the lecture? Do you remember function composition? No? Uh-oh. That's not good. We need to understand function composition. Let's do a really concrete example here. So I've got A. We'll do 1, 2, 3, 4. B is going to be the elements 5, 6, 7, 8. and C is going to be the elements 9, 10, 11, 12. Okay, so here's the different sets. My function f might map 1 to 6, 2 to 5,
Oh yeah, I remember.
3 to 7, perfect, 4 to 8. My function, so here's f right here. My function g might map 5 to 11, 6 to 9, 7 to 10, 8 to 12. Now, based on my picture up here, really quick, tell me what's f of 1?
10 or 9?
6. F of 1 is 6. F maps 1 to 6.
F. Okay.
Yes. Let's try another one. Tell me what g of 6 is. 9. G of 6 is 9. So now what you were jumping ahead to in your head is if I ask you now, what was g composed of f? G composed with f of 1.
9.
Then it's ultimately going to be 9. But how do we interpret this? When you see g composed with f of an input, that's always interpreted as g of f of that input. And then f of 1 we found out was 6. So f of 1 is the same thing as 6. And then g of 6 we found out is 9. So g composed with f of 1 is 9. So composition is a way of doing two functions in one go. Instead of mapping 1 to 6 to 9, function composition maps 1 directly over to 9. And we can do it for all the other elements. That's function composition, combining two functions together into one. All right. So with that, let's jump now into permutations. What's the definition of permutation? Let A be a set. Then a permutation on A is a function f from A to A such that f is a bijection. So A sum set, f is a function on A, so it maps everything in A to something else in A. And it does it as a bijection. Do an example really quick. Here's a set A, here's a set A again. We'll say that A has a set 1, 2, 3, 4. 1, 2, 3, 4. Possible bijection would be mapping 1 to 2, 2 to 1, 3 to 3, 4 to 4. There's a possible bijection F. F is now a bijection on, or permutation. F is now a permutation on A. It's also a bijection. Did we use up all of this set? Yeah, so it's on 2. Is it 1 to 1? Okay. What if instead of mapping 2 to 1, I also map 2 to 2? Would this be a permutation on A?
No.
No, why not?
Because it doesn't take all.
It's not a 1 to 1.
It's not 1 to 1, and it's not on 2, so it's not a bijection. So in order for it to be a permutation on A, it has to map everything in A to everything in A in a 1-to-1 way. Good? Feel like you understand the definition there?
Okay, so wait, can you give an example of why function and one-to-one are different?
Sure. This right here is a function. F is a function from A to A. It's not 1 to 1.
Because, wait, no, it's not even a function.
It is a function.
No, because 1 has...
1 maps to 2 and 2 maps to 2, that's fine.
But
We don't have one input going to two different things. How would I make this not a function? It would be if I had 1 also go to 1 like that. Now it's not a function. I can't have 1 goes to 2 and 1 goes to 1.
So it's not one-to-one because both 1 and 2 are on 2?
It's, if we erase this arrow here, it's not 1 to 1 because 1 maps to 2 and 2 maps to 2. What does 1 to 1 mean? It means same output implies same input. But look at this. Notice that in this case, f of 1, what's that equal to?
2.
Is equal to f of 2. F of 1 and f of 2 both map to 2. So those outputs are equal. F of 1 and f of 2 have the same output. Does this imply that 1 is equal to 2?
Oh, no.
No! This implication is false. So this function is not 1 to 1. If this implication is always true, then the function is 1 to 1. If the outputs are the same, the inputs better be the same. Otherwise, it's not 1 to 1. This one says if the inputs are the same, the outputs better be the same. Otherwise, it's not a function. Good. Any other questions about that? Feel like we're understanding these words?
Yeah.
Okay. So we're all good with the definition of permutation? Fantastic. All right. So now let's look at a concrete example of a permutation. So let A be the set 1, 2, 3, 4, 5. And pi, now as a general rule, this, I know you're used to thinking of pi as the real number 3.14159, da 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 da. Pi here is going to be a variable. In general, here's the variables we're going to see over and over again. You're going to see me use pi, sigma, tau, and iota. We typically use lowercase Greek letters to represent permutations. Just American mention.
So what does each variable represent?
That's like asking what does x and y represent when you're doing algebra. They're just variables, they just represent numbers. Here, anytime you see one of these variables, they're going to represent permutations. The only one that's going to be special is iota will always use for the identity permutation. The permutation that maps 1 to 1, and 2 to 2, and 3 to 3, and 4 to 4. So this one will always be the identity one, but these ones we'll just use as variables however it's convenient. So from here on out, remember, lowercase Greek letters, always and forever, for this lecture, are going to represent permutations, not numbers. Okay. So we're going to let pi be the permutation. 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. First off, is pi a permutation? Is it a permutation on A? Notice that A is a set 1, 2, 3, 4, 5. You see that?
Yes.
So A is a set 1, 2, 3, 4, 5. So notice it maps all of A. 1 goes to something, 2 goes to something, 3 goes to something, 4 goes to something, 5 goes to something. Check on the right hand side. Do we use everything? 1, 2, 3, 4, 5. So yeah, maps everything in A to everything in A. So it's it's permutation. Now, let's know something. Looking at, I've used apps.
Meant to use pies.
Yeah. It's because I don't work with permutations all that much, and so I always just think a function. I probably did that a lot throughout this lecture. Hopefully not. Hopefully I remember to use pies and not f's. Okay, anyways. So, notice now, let's look at a list of all the outputs. So this is a list of all the outputs of this permutation. So we're going to look at what did 1 go, what did 2 go, what did 3 go, what did 4 go, what did 5 go to.
Output or input?
The input's 1. When I run it through the function, it's the output. So I'm saying this is pi of 1 is what 1 mapped to. So this is what 1 mapped to, what 2 mapped to, what 3 mapped to, what 4 mapped to, what 5 mapped to. Okay? We're just writing it as a list. In this case, when pi is this function right here, then that list is 2, 4, 1, 3, 5. Because pi of 1 was 2, pi of 2 was 4, pi of 3 was 1, pi of 4 was 3, pi of 5 was 5. So in that case, it came out like this. But for any permutation I were to write out on A, so it mapped 1 to one of the elements, 2 to one of the elements, 3 to one of the elements, 4 to one of the elements, 5 to one of the elements. For any permutation I had on A, if I wrote out this list right here, what are the numbers that are always going to be in this list right here? It's going to be the same numbers 1, 2, 3, 4, and 5 again. Just potentially in some different order. You see that? And that's intuitively what a permutation does. You take the numbers and you run it through the permutation and it just reorders them. So you typically, the way that you've used the word permutation in just English prior to this class, you just thought about a permutation as just a reordering. When you count the permutations, you count all the orderings. And so that's what a permutation ultimately does, is it just reorders the same objects. And that's good intuition to have in your head for a permutation. So in this case, this right here, 2, 4, 1, 3, 5, it was just a reordering of 1, 2, 3, 4, 5.
And that's how you prove it's a permutation, if it can do that.
That's what a permutation is. It maps everything in a set to everything in that set again in a one-to-one and onto way. It's a bijection from the set to the set. And so, yeah, when you list out all its outputs, it's always just going to be a reordering of the inputs. So when you're talking about how many ways can I arrange 5 objects, you're asking how many permutations can I create for a 5-element set? It's the same question. Because a permutation is just one reordering. That make sense? Okay. So let's just go through this really quick while we're on this train of thought to tie us back to older thinking. So if I have a permutation on the set 1, 2, 3, 4, 5, what does that permutation look like? It's going to map 1 to something. It's going to map 2 to something. It's going to map 3 to something. It's going to map 4 to something. Oops, sorry. And it's going to map 5 to something, right?
Yeah.
That's what a permutation on the set 1, 2, 3, 4, 5 is always going to look like. How many options do I have for what can go here? 5 options. I can put the number 1, 2, 3, 4, 5 there. How many options do I have for what can go here?
4.
Now we only have 4 options, because one of our options was used in pairing it with 1. So now we have 4 options for this. And how many for this?
3.
And for this? And for this? And so how many options, how many possible permutations can I create? 5 factorial. That's why we say factorial counts the number of permutations, or counts the number of ways that you can order the objects. How many ways can you order 5 objects? 5 factorial ways. How many permutations are there with 5 objects? 5 factorial ways. Same exact question. So a permutation, this is a mathematical object that we use for a reordering. If you want a precise definition of what we mean by reordering, here's what we mean. A permutation. Now you have a precise definition for that. Whereas before, reordering was just some high-level English term.
Well, does your inputs have to always be ordered?
No, it doesn't matter. But you say the first object is now going to be 5 if you put 5 there. This right here is a set. Order doesn't matter in set. If I were to swap those 2 elements, so if I put 2 goes to something here and 1 goes to something here, it doesn't change anything because we didn't change the function.
So down there on your note, you made a list on purpose?
Yes. If we were to create a list of the inputs, here's a list of the inputs, then run it through our permutation, like this,
Okay.
we would get a list of the inputs just in different order. Because a list is keeping track of order, right? So list out your inputs. There's one ordering. Now when you run it through a permutation, it gives you a new ordering. Count all the possible permutations you can run it through. That's all the possible reorderings you can have of your inputs. Make sense? Cool. All right. So we kind of jumped ahead since we were on train of thought there that I didn't want to abandon. So while now we can still answer that. Okay. So we got that a permutation is just a ordering. And counting permutations, counting the number of orderings. All right, definition. Given a set, A equal to 1, 2, 3, 4, all the way up to n, we're now going to use S sub n as the set of all permutations on the set A. The set of all possible permutations on the set A.
What is that?
And it doesn't matter, it's just a... Yeah. Just a variable that we can use. So let's try to understand this, make sure we understand. Let's say that A is equal to the set 1, 2, 3. There's A. So then what is S sub n? S sub n is the set of all permutations I can create on the set on A 1, 2, 3. So one possible thing in here would be the function that maps 1 to 1, 2 to 3, and 3 to 2. Here's one possible permutation on that set. Right? And I could write out another permutation. And another one and another one. How many could I write out if I wrote them all out?
3 factorial.
Or 6, right? Yeah, 3 factorial. So, sorry, this is not S sub n. This is now S sub 3.
Oh, okay.
Right? And now if I wrote S sub 10, that's a much bigger set.
Why is that not S sub A? That seems so much simpler.
Because we don't want to have to define the set A. If I just show you S sub 3 out of the blue, then you instantly know we're talking about all the permutations on the set 1, 2, 3.
So it always takes the first one.
It's always just counting up to that number. So forget that I ever put this A here. If you see S of 3, you instantly know it's talking about this set of permutations. And if you see S of 10, now you instantly know it's talking about the set of all the permutations you can create on the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how big would this set be?
Does it have to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Or can
Yes.
it just be a list of 10 numbers?
Not a list, a
Or
set.
A set.
A set, and it's a set of, it can be any set of 10 things, but we just relabel those 10 things now. I'm just going to arbitrarily relabel one of those things as 1, and relabel another one as 2. And relabeling doesn't change anything. Right? If I suddenly call you Frank, Hank, and Dorothy, it doesn't change anything about what you are.
Right.
It's just a relabeling. So yeah, you can just, if you have a 10 element set, you can just relabel the elements as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and be on your merry way. Or we just have a lot of confidence in your ability to figure it out.
I like that answer better. Not that good about it last night, but
All right, it's wonderful. All right, yeah, let's do a quick recap of the permutation so that we're all on the same page. Do you remember what a function was?
yes.
Do you remember what a bijection was?
On to and
Yeah, so if I have f is a function from a to a, and I tell you it's a bijection, then you know it maps everything in A to everything in B in a one-to-one way,
okay.
right?
Yeah. Did you mean to write A to A or A to B?
I wrote A to A on purpose.
But you said
We could have said A to B, that's fine. Oh, did I accidentally say B?
Yeah.
Oops. So if I tell you f from A to B is a bijection, then you know it maps everything in A to everything in B, and it does it in a one-to-one way.
Okay.
If I tell you f from A to A, so the same set now in both places, is a bijection, then it mapped everything in A to everything in A in a one-to-one way. This is what we mean by permutation.
Couldn't you?
And we would call that a permutation on A. It's a bijection from A to A.
How is that any different from the identity?
Give you a quick example, but let's read the definition, make sure you got it. So let A be a set, then a permutation on A is a function, f from A to A, such that f is a bijection. Good? All right, how's that any different from the identity? Let's give you an example. Let's say, typically when we talk about permutations, we use Greek letters for them. Pi, sigma, tau, and iota are going to be the ones that we use the most. So here, pi is going to represent permutation. Pi is a function that maps 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 5.
All right.
So A, sorry, didn't start with A. A is a set 1, 2, 3, 4, 5. Now pi is a function from A to A, and notice it's a bijection. So it didn't necessarily have to be the identity function. The identity function is just one possible permutation.
Okay.
How many possible permutations are there on this set?
It's like 5. I want to say factorial.
It is 5 factorial. Because think about it. Every permutation has to map 1 to something, 2 to something, 3 to something, 4 to something, 5 to something, right? How many options do we have for what we can map 1 to?
You got 5.
Then we use that one. How many options do we have for what we can map 2 to?
Then you have 4.
And then 3, and then 2, and then 1. And that's where the 5 factorial comes from. So you're exactly right. And so now one more piece of notation. When you see me write S sub 5 now, this is shorthand for the set of all possible permutations on the set 1, 2, 3, 4, 5. So this is a set of functions. And one of the functions that would be in the set is the pi that we have written over here. Here's one of them. This would be in the set.
Okay.
And then obviously there's 5 factorial things in this set, and I'm not going to write out all those functions. But listing out all those functions is what we would mean by S sub 5. And another function that would have been in here would have been the identity function, which mapped 1 to 1, 2 to 2, whatever. That would have been one other permutation in there. Right? So that's a quick recap. If you're watching, the intro will probably do some good, or maybe you'll figure it all out and jump in from there. Okay, so given some set A equal to 1, 2, 3, 4 all the way up to n, S of n is the set of all permutations on A. The identity function on A, typically written as iota, that's iota, it's like a lowercase I without the dot above it. Iota is the identity permutation. So from here on out, anytime we use iota, not only is it a permutation, but it's the identity permutation. And so, instantly, if I tell you that iota is in S sub 3, what is iota?
1 to 1, 2 to 2, 3 to 3.
It's a function that maps 1 to 1, 2 to 2, 3 to 3. If I would have told you iota was in S sub 20, then it would have been the function that mapped 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, all the way up to 20 to 20. Make sense? So from context, you instantly know what iota represents based on the set it comes from. It will always specify which set it comes from. So from here on out, we're going to be talking a lot about sets of permutations. And so then we'll talk about the identity in that set of permutations, and we always know what the identity is. Make sense? Okay. So the identity function on A, typically written as iota, is a permutation. Example, if you know that iota is in S sub n, then you instantly know iota is equal to 1 goes to 1, 2 goes to 2, 3 goes to 3, dot, 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 all the way up to n goes to n. If we replace that n with 50, then we do this all the way up to 50, goes to 50. Wonderful. For example, if you know iota is in S sub 5, you know iota is equal to the function that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. Okay.
So the numbers, like the elements in it, the fact that they go from 1 to 2 to 3 to 4 actually matters to this.
No. Because you can always relabel a set. If you were to give me a set of square, triangle, heart, and I want to create a permutation on this set, terrible heart, we'll do star, so we don't have a lot star in class. All right. If you talk about, I want to create a permutation on this set, we can just relabel the elements. And say, I'm going to call the square 1, I'm going to call it the triangle 2, and I'm going to call the star 3. And I can always do this kind of relabeling. It's something we talked about last class.
Okay.
And it doesn't change anything. And as you walked in, I was explaining to them, I could call him Frank, Hake, and Dorothy. It doesn't change anything about him if I just give him different names, different labels. If I was talking about the set of them and I give them different names, it doesn't change anything.
All right.
So since it would just be a relabeling, it doesn't matter. So you can still talk about permutations on anything you want. You just need to call one of those things 1, one of those things 2, one of those things 3, for all this to follow. Okay. So I told you what we're going to be interested in mostly now is sets of permutations, S of n. Hayden. All right. So let's look at some of the properties on S of n, on sets of permutations. First off, what is the size of S of n? How many permutations are in S sub n?
N factorial.
N factorial. That make sense to everyone? Okay. Property number 2. For all pi and sigma in S sub n, sigma composed with pi is also in S sub n. Given any two permutations in the set, it is always the case that their composition is also in the set. How do we know that?
Because it only contains the elements within it. It's every possible set of elements.
How do I know that when I compose these together, so maybe this one's 1 to 1 and maybe this one's 1 to 1, but maybe composing them together isn't still 1 to 1? This one's a bijection, this one's a bijection. How do I know that composing them together is still a bijection?
Oh. Okay.
Is that something we automatically get for free through function composition? It is?
I don't know. I just
Not necessarily.
Not necessarily. So how can we validate that this is the case? Let's think it through really quick. So all I'm trying to make sure is that sigma composed with pi, how do I check if it's a permutation? I need to check 3 things. 1. Is this a function from S of n? All the permutations in here are going to be functions on the set 1, 2, 3, all the way up to n, right? So first off, is this whole function, when I compose these together, is this going to be a function on this set to the set?
Yes.
Yes. How do we know?
Because it's in it.
What's the domain of this function going to be?
It's going to be n.
It's going to be all these elements. So it definitely maps from all of these, right? Now does it map to all of these?
It should if it's permutation.
It should. How do we know it does? Well, if this function, we know pi is 1 to 1, and we know sigma is 1 to 1, and we proved last week that if two functions are 1 to 1, their composition is still 1 to 1. Right?
Say that again.
We know that this function is 1 to 1.
Yeah.
We know that this function is 1 to 1. We proved last week that the composition of 1 to 1 functions are 1 to 1. If this maps all inputs to one and only one output, and this maps all inputs to one and only one output, if this always goes to unique outputs and this always goes to unique outputs, their composition is always going to go to unique outputs.
Okay.
That's what we proved last time. So I know that the composition is 1 to 1. The whole composition is 1 to 1, right? I know it is mapping from this set. And since it's mapping from this set to this set in a 1 to 1 way, the only way to do that, since these are finite sets, is to map every element to ultimately every element.
Because they're the same size.
Because they're the same size. So it's on 2. So it's 1 to 1 and it's on 2. So it's a bijection.
Yep.
Make sense? That's how we know it's a bijection. So I know that this is a bijection. The only elements it has to operate with are the same elements that these have to operate with. So it's in a bijection with those elements. So it's in the set of permutations. Okay, let's look at this one. Given 3 permutations, pi, sigma, and tau, then we know that tau composed with pi composed with sigma, or sigma composed with pi, is the same as tau composed with sigma composed with pi. We also proved this last week.
Yeah, we did.
We proved that composition is associative. Make sense? Wonderful. Now let's look at this one. This one says for every permutation, the identity composed with that permutation is the same thing as that permutation by itself, is the same thing as that permutation composed with identity. We also proved this one last week. Composing with identity functions at the start or the end doesn't change the function. You remember that? No? Let's make intuitive sense of this one. So we'll do this on the set 1, 2, 3, 4. 1, 2, 3, 4. And we'll make up some permutation. Here's some permutation. 1 goes to 3, 2 goes to 2, 3 goes to 4, 4 goes to 1. Here's a permutation, right? What would the identity permutation do? It just maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. Or 4 to 4, sorry. Here's pi, right? So there's pi by itself. If we do iota, if we do pi composed with iota, what does that do?
1.
Iota first maps 1 to 1, right?
Yeah.
And then we run through pi.
1 to 4. 1 to 3.
So iota would just be really quick mapping 1 to itself first, and then running it through pi. Similarly, it would be mapping 2 to itself first, and then run it through pi. 3 to itself first, run it through pi. 4 to itself first, and then run it through pi. Which is the same as just running it through pi. Am I losing you? That make sense? Similarly, if we did iota composed with pi, what does that do? That just maps the elements to themselves at the end. So if I run my function through pi, if I forget doing these loops first, if I just run 1 through pi, so 1 goes to 3, and then after that I map 3 to itself again, does that change anything? No. Similarly, if I map 4 to itself at the end, or 2 to itself at the end, or 1 to itself at the end. That's what this would be doing.
Okay.
So if I do pi, then the identity function, that's the same as just doing pi, which is the same as doing pi, or doing the identity function and doing pi. Doesn't change anything. Good with this one?
Yeah.
And then finally this one. This one says that for every permutation, there is an inverse permutation in S of n. And pi composed with its inverse is going to be the identity function, which is the same as the inverse composed with pi. Let's make sure that we understand this one. First off, if pi is a permutation, then it's 1 to 1 and on 2, right?
Yeah.
And so its inverse, what does the inverse do? If we did pi inverse, it just runs the arrows backwards. It maps 1 to 4. It maps 2 to 2. It maps 3 to 1. It maps 4 to 3. Just runs the function backwards. Right?
Yeah.
So it's still going to be 1 to 1 and on 2. So it's still a bijection. So when you have a bijection, its inverse is still a bijection. So the inverse of a permutation is still a permutation. Right? And then, I don't know if this one makes obvious sense to you. A function composed with its inverse is the same as identity function. Pi was mapping this way. Pi inverse undoes it.
Oh, got it.
So I start at 1. I run pi, which gets me to 3. Then I run pi inverse, which gets me back to 1. When it's all said and done, what did I do? I mapped 1 to 1. Similarly with 2, with 3, with 4. I could also start over here. I can start with 1, run it through pi inverse, which gives me 4. Then run it through pi, which gets me back to 1. So, doing pi then pi inverse is the same as doing pi inverse and pi is the same as just the identity function. Make sense there? Now, I'm going to take a second to draw a couple parallels here. And maybe write this a little bit different. For all x, y, and r in the real numbers, comma, x plus y is in the real numbers. Gonna rewrite this one. For all x, y, and z in the real numbers, x plus y plus z is equal to x plus y plus z. Rewrite this one. For all x in the real numbers, comma, 0 plus x is equal to x plus 0.
Oh, that makes so much sense.
Rewrite this one. For all x in the real numbers, comma, there exists, I didn't write the there exists here, there exists pi inverse in there. There exists x inverse, we'll call it negative x in R for its inverse, such that x plus negative x is equal to 0 is equal to negative x plus x. You see the similarities between this and this? And it's a common property. So the fact that we're using an operation in permutations here, instead of real numbers with an operation plus here, different operations, different numbers, but you see those parallels, these same set of properties show up a lot again for a lot of different things. And there's an abstract way that we can just talk about these properties. Is there a way that I can talk about both of these at the same time? That's what you do in abstract algebra. That's why I meant that the one time again that we might see permutations show up again is in abstract algebra in noting those properties. So, interesting similarity there. Point that out for you.
Is abstract algebra a class?
Yes, abstract algebra is a class. One of the sections that we'll be going over, one of the chapters that we'll potentially be going over in this class is like dipping your toe into abstract algebra. You start that with groups. And what I just showed you, that's a group, this is a group, and a group is a group. And you can prove things about groups, and the things you prove about groups are going to be true for this, and they're going to be true for that. Because they're both just groups. It's a whole nother level of abstraction.
Okay.
And it's amazing. You could be proving things that happen to be true for permutations when you're talking about composition, or for real numbers when you're adding. Same thing. Kind of. There's a way that you can view them as the same thing, if you limit how you talk about them. Anyways, that's why we're knowing these properties here. Very useful properties. When these properties show up, not necessarily one, but these ones down here, when those properties show up, you notice that they show up with a lot of sets and a lot of operations. Okay, now a permutation, we know, is this big function right here. Look at this for writing a permutation on just a set 1 through 5. This is annoying. That's a lot of writing for such a simple function. We need better notation. So we're going to try and come up with some better notation here. So pi, this is going to be the same pi that we have written here. I'm going to try and write this a little bit cleaner. Pi, we'll just write it like this. Here's our inputs, 1, 2, 3, 4, and 5. Here's our outputs, 2, 4, 1, 3, and 5. So 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5, right? Now notice that when we write pi out like this, the top row is always just going to be the numbers 1, 2, 3, 4, 5. So we don't really need to write the top row. So we can just write the bottom row. And so if I say pi is equal to this thing, then we know 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. Because 5's in the 5th place, so that's what 5 went to. Since 1's in the 3rd place, that's what 3 went to. So here's some more concise notation for writing this thing right here. With me so far? Sorry, what?
Do you have to include the or?
No, I'm just saying we could write it like this, or we could, if we want to, instead write it like this.
And you just assume that the first one's 1, 2, 3, 4, 5.
Yeah.
Okay.
Well,
So-
we know it is.
Huh?
We know it's one.
We agreed to that as a matter of convention, and so from here on out, you would instantly know what this was. If you were looking at this and I said, what did 4 go to, what would you tell me?
2.
Or
Oh, 3, sorry.
Oh, 4 goes to 3.
4 goes to 3, right?
Yeah.
What did 1 go to?
2.
What did 2 go to?
4.
Okay. So, you see how this is a much easier way of writing this, and you'd much rather write this on your homework than this,
Yeah.
right?
Good.
Now, let me ask you a question. So let's look at this permutation. Let's say instead pi was equal to 1, 3, 7, 9, 12, 6, 4, 8, 2, 7. And I say, what does 6 go to? Ah, you see what you're doing now? Oh, that's kind of annoying. So this notation, sorry, I didn't put any comments there.
You have 2 7s in there.
Thank you. Whatever. Pretend I wrote one okay. The problem is, when the permutation gets really long, imagine I wrote a permutation with 100 elements in there, and I said, okay, now what does 33 go to? That's super annoying, right? You don't want to have to do that. So we're still going to try and come up with even more concise notation. And now the concise notation we come up with is called cyclic notation.
Cyclic.
I'll make the cyclic notation make sense here in a second, but here's the way that you read it. So you do a parenthesis, and then you always start by writing 1. As a matter of convention, you can put any of the numbers that we're talking here, 1 through 5. You can write any one first. As a matter of convention, we write 1 first. You don't have to. So first we write 1. Then the next number is what 1 maps to. So look over there, what does 1 map to? 2. So 2 is the next thing we write. Now what does 2 map to? 4. So that's the next thing we write. What does 4 map to? 3. So 3 is the next thing we write. What does 3 map to? 1. So that would take us back to where we start. If it takes us back to where we start, we write a parenthesis, then we write a new parenthesis, and we write the next number that we haven't used yet. The next number that we haven't used yet is 5. What does 5 go to?
5.
So we end the parenthesis. Now look at this notation. Really quick, what does 4 go to?
3.
What does 1 go to?
2.
What does 3 go to?
1.
You see how this is much easier to read?
Yeah.
And even if I give you some massive permutation, which had 1, 3, 2, 5, 7, 4, and parentheses, then start out here, 11, 2, whatever, and went on its merry way. If I really quick to ask you, what does 7 go to?
4.
You can instantly tell me. You see that?
So isn't that a lot more work to write?
It's about the same amount of work to write. Here we have to write out 5 numbers. Here we have to write out 5 numbers.
Except for there you have to write brackets, so it's less work to write parentheses.
but we'll do more parentheses than we will brackets here. So in terms of writing, it's about the same part, but it's real easy for you to tell what comes next, and you don't have to start counting what position it's in. So that's why we use cyclic notation, and this will be the way that we do it.
Can you say that slow?
Huh?
Cyclic? What are you saying?
Cyclic, as in cycles.
Cyclic.
Cyclic.
Is that?
It's very cyclical. If it has lots of cycles, it's very cyclical. It's cyclic notation.
Cyclic.
Why isn't it just cyclic? Like cyclic. Cyclical.
Is it the or the?
The.
Oh, it's-
How you and then-
It's the sometimes.
How you choose to pronounce a word is how you choose to pronounce a word. And that comes and goes with time. Pronounce it however you want.
The and the are different for grammar rules. There's like a rule that makes it the. There is. It has to do with a vowel coming after it. It's the same thing with and the. Or and A, yeah. You
The
have
and
A
the are
plus
spelled identically.
I know,
Okay.
but you have to pronounce it differently according to grammar rules.
There are conventions. Conventions that come and go. And what's the right way to enunciate a word? It's going to be whatever the culture that you're currently in says. Words change with time. How you pronounce them changes with time. And so you often have words that, when you say it, and give you one example. You know what a coincidence is?
Yeah.
We don't call it a coincidence, we call it a coincidence. Although we're talking about things that coincide. So when you say coincide, you say coincide. And now when you're saying it has the property of coinciding, you don't call it coincidence, you call it coincidence. And you enunciate it different. You pronounce it different. Why? There isn't rhyme or reason to it. It's just people happen to do it differently. And so people will come all along later and try to come up with rules that capture how people happen to be talking. But how people talk changes. So rules come and go. And so how you pronounce it, I could care less. Call it cyclic, call it cyclic, I don't care. It makes no difference. Right? Why is it cyclic and not cyclic?
Because cyclic is the.
Why is it coincidence and not coincidence?
Because you sound like a dummy if you say coincidence.
Just because it sounds strange to you. But if you grew up in a culture where everyone said coincidence and you start going around saying coincidence, there's like, why are you saying it weird?
Well, it's kind of like when people say, like, entrepreneur. They sound like a little kid. It's an entrepreneur.
Well, that
because
changes
the
the
vowel comes
spelling.
after.
Okay,
It's very.
doesn't matter.
Sorry.
Call it whichever you want. Okay. Now, why is it called cyclic notation? That is because we're looking at cycles. So now let's look at the graphical representation of the function. So when we create a graphical representation of the function, again, as a matter of convention, start with the node 1. Here's 1. What did 1 go to looking at our function? 2. So draw a circle with 2 in it with an arrow pointing to 2. Now what did 2 go to looking at our function? 4. What did 4 go to?
3,
What did 3 go to?
1.
1. And so you see that you have this cycle here.
What is
So this is a cycle, and this is a cycle, same thing. So we call this a cycle. And we call it cyclic notation because you're writing out all the different cycles. And when you look at that 5 goes to 5, we draw that graphically like this.
What?
What if
What is
one
that?
went directly to
What if
4?
it doesn't do that?
What if it doesn't do that? We'll come to that. What else did you say?
What if one goes directly to 4 and skips 2? You go back to 2 when you hit 3?
Well,
Or
a number
you go
was
no, you
two,
move
so
it.
whichever
You move
number
Yeah,
forward.
it
just move the
You're
order.
saying, what if-
You move it forward.
No, that's not in the.
What if 1 went directly to 4 instead of to 2?
is. You just change the cycle.
You changed.
Is that what you're saying?
You switch it.
Let's just follow through his example. We don't need to all talk at the same time. Let's change 1 to point at 4 like this. And what else? Just leave it like that?
Well, then you follow the cycle, but 4 goes to 3, not 3 to 4.
Oh, so now you say you want 4 to go to... Oh, did I draw that arrow backwards?
Yeah.
Oh, no wonder you guys are confused. That arrow's backwards. Should have been like that. Sorry. Did that clear up a lot? 4 goes to 3. So you're saying what if it looks like this?
And 2 goes to itself.
And 2 goes to itself?
Yeah. How do you write that?
Just like that.
Perfect. So this is a perfectly valid permutation,
Yeah.
right? Okay. Let's write that out in cyclic notation. Start with 1. we have 1 goes to 4, goes to 3, goes back to 1, end.
Okay.
Now, what's the next lowest number that we haven't used yet?
2.
2.
Next lowest.
Yeah.
Okay.
As a merit convention, just pick another number you haven't used yet. As a merit convention, we like to pick the smallest one. But it's just convention. Okay, so 2. What does 2 go to itself? End. What does 5 go to itself? End. There it is in cyclic notation.
But what if 2 and 5 went to each other? You just
Get rid of the parentheses in
get
there.
rid of the parentheses.
So yeah, 2 happen to go to 5, and 5 happen to go to 2. Then now, 2 goes to 5, and 5 goes to 2, so in parentheses. Now, what if you happen to get a function that you can't draw as a graph like this? What if you get one of these functions that when you draw it out, it isn't a graph of cycles?
Then it's not permeable.
Then it's not permutation. It's either not onto or 1-to-1. Because if we tried to do something like, let's go back to a picture kind of like what we had before. Let's say, what if 1 went to 4, but also we had 2 went to 4 right like this. So 2 is not part of a cycle anymore. Why do we know this is impossible?
Because it can't be.
We have 1 going to 4 and 2 going to 4. We have 2 things going to 4, so it's not 1-to-1. So you can't get a picture that looks like this. Because it's not 1-to-1, because we have 2 things going to 4.
So if our graph doesn't cycle that we're doing, then it's not permeable.
Yeah, if you get some function and you try to draw it out as a graph, and it's not creating just cycles, then you don't have a permutation.
Okay.
Okay, so let's make sure you're getting this notation. Okay. First off, here's our permutation that we have written up here. Let's write out its inverse permutation.
How do you want us to write it?
So we're going to use the same notation here. Try to give you a hint as to what notation we're going to use in each case. 1, 2, 3, 4, 5. How many are there? 9?
Yeah.
6, 7, 8, 9. Let's write what each of them go to. So looking, here's pi. We're doing pi inverse. What does 1 go to?
7.
7. Is anyone confused how they got 7? Since 7 went to 1 here, 1 goes to 7 here. It's the inverse. We're flipping it. Right? What does 2 go to?
1.
1. What does 3 go to?
5.
Next.
8.
8 or 6?
8.
Okay.
3,
Oh, you got me confused and I lost my spot.
Huh?
You got me confused and I lost where I was.
Good.
2.
Rethink about it, re-understand it. What does 7 go to? 2. What does 8 go to?
6.
What does 9 go to?
9.
Wonderful. And when it's all said and done, we better have 1, 2, 3, 4, 5, 6, 7, 8, 9 on the bottom, or we did something wrong. All right. Now let's re-represent this function right here, this time using cyclic notation.
Okay.
With me?
Yeah.
All right. What number should we write first?
1.
1. American convention, just start with 1 every time. What does 1 go to?
7.
2.
We're doing pi,
Oh.
not
Oh.
pi inverse.
2.
2. Which goes to?
7,
Which goes to?
1. Oh,
Oh.
it goes to 1.
Goes to 1. So we end our cycle, right?
It's tricky.
Yeah.
Now we start our next cycle. What number am I going to write?
2.
3.
Yeah, that. 3.
Good.
5,
3. What?
Yeah,
3,
5.
5.
Dude.
Oh, okay. 3 goes to 5 goes to?
Close
N.
parenthesis.
Goes to end.
What? Oh.
4,
4.
6,
6.
8,
8.
4. Oh.
Wait, what? 6?
Close.
Never mind.
4 goes to 6, goes to 8, goes to 4, so parentheses. Now what?
9 to 9.
7. Oh.
7 goes to 9,
No,
goes
9.
to 9, and 9.
Right.
Good?
Yeah.
Now we just wrote it out in cyclic notation. Now, let's write the inverse in cyclic notation.
Okay.
7? Or
1 goes to 7.
We want to start with 1.
Oh.
Okay. Now what?
7.
7. 7,
2,
2.
1. Oh, and parentheses.
Wait, hold on, slow down. What? Oh, on the
We're doing pi
right.
inverse.
Right.
Can you see my -1 here? So -1.
Okay, now we can start with 3.
And then 3 and 5 again.
Yeah, 3 and 5. Can't reverse this one.
Right,
Wait, there's
Four.
3.
4 to 8.
4, 8, 6,
Anyone arguing with her?
and then
Nope.
9.
And then 9.
That was confusing, by the way.
Confusing a little bit.
Yeah,
That just
but
changed
no, it's
2 and
fun.
7 and 8 and 6.
Yeah, I didn't change that much about that.
Yeah, you see that we didn't have a huge difference between these and these, which is fine. But you kind of notice it was kind of a pain to go from pi to figure out pi inverse, right?
Mm-hmm.
To then figure out pi inverse this way.
Yeah.
What if I just knew pi was this? Because here's the way that we're typically going to write pi, right? I just want to be able to look at that and figure out what pi inverse is.
Okay. It's easy.
How's it easy?
You just have to think about it.
You just have to think about it. What
If
does the
2 goes to
inverse
7.
do for a function?
It flips all the numbers.
It flips all the arrows around. Instead of, so right here we have a graphical representation of this function, right? Here is a graphical representation of pi. I have it written out for you. 1 goes to 2 goes to 7, goes to 1. 3 goes to 5 goes to 3, whatever. 4 goes to 6 goes to 8, 9 goes to 9. You see that?
Yep.
Inverse of pi would be to flip around all those arrows.
Mm-hmm.
That would be its inverse. Does that make sense to everyone?
Yes.
Notice that if I flip around the arrows on this loop, does that change anything?
No.
If I flip it around on this loop, does that change anything?
No.
No. And it's going to keep the loops the exact same when I flip the arrows. If these three together were creating a loop, they're still going to create a loop when I flip around the arrows.
Mm-hmm.
So we expect, in cyclic notation, the inverse to kind of resemble the initial function. And so in cyclic notation, what do? We just write the cycles backwards. Instead of the cycle going 1, 2, 7, when we do it backwards, it's going to go 7, 2, 1.
Oh.
Yeah, you can do that one too.
You can do it that way too. We'll do what you're saying here in a second. But the reason I said it that way is it's literally just looking at those numbers backwards. This is 1, 2, 7, write it backwards.
Oh,
7, 2, 1. Write it backwards. 5, 3.
What was the
Write it backwards. 8. This is the inverse.
Wait, 8, 6, 4. That
Yes.
would be 6, 8, 4.
No.
So what did I do here? I just wrote the same. Was I looking at the right function? I was looking at this, hopefully. 7, 2, 1, 5, 3, 8, 6, 4, 9. Okay.
I was looking
So
at the wrong function.
Okay.
I was looking at the inverse.
6, 8.
So I just took pi and wrote all its cycles backwards. This said 1 goes to 2 goes to 7. I says no, we're going to have 7 goes to 2 goes to 1 goes to 7. You see how writing it backwards is equivalent to just flipping around all the arrows?
Yeah.
Which is a really, really easy thing to do.
But when you...
Now you're saying, but I want the 1 to go first rather than the 7. Right? If we shift our whole cycle 1 unit to the right, it doesn't change anything. So it's still identical. So you can shift everything if you want. So here's a quick way to get the inverse. Now you can just shift elements.
1, 7, 2.
Because 7 goes to 2 goes to 1 goes to 7 goes to 2 goes to 1. I can write that as 1 goes to 7 goes to 2 goes to 1. Right?
Yeah.
So you're just shifting the cycle over 1, which will give you this. Notice that this and this say the exact same thing. This says 1 goes to 7 goes to 2 goes to 1. This says 1 goes to 7 goes to 2 goes to 1. So you can just shift it over 1. Shift it over 1. If you shift it to the right, you just take your thing that falls off the right and comes around. It's like these things are circled around together. Because remember, 1 goes to 7. It's like it's a circle around. So you just shift everything 1 unit to the right, which would push the 1 over here. Shift everything 1 unit to the right, which pushes the 3 over here. Shift 1 unit to the right, which pushes the 4 over here. So that's a fast way to calculate these inverses now.
But we don't have to shift it so that 1 comes first.
No, this is a fine way to write the inverse.
Okay.
But you can't do homework?
Huh?
But you can't do that in homework? You don't have to put the
Yeah,
one
this would
first.
be a fine way to do it.
Awesome.
So now, you have a super quick way of coming up with the inverses of these functions. I give you a function like this, it takes you 2 seconds to write out its inverse. You can write it out like that. Right? Super easy. Okay. Now, transposition. Before we get into this, let's try and give some intuition for these things. Erase some of this down. So, if we're looking on the function, if we're looking on the set 1, 2, 3, 4, 5, what is the simplest function I could possibly write on that set? The identity function. The identity function, which is written out in cyclic notation, the identity function is 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5. That is the simplest function we could possibly write on there. Let's actually write it out this way so we can talk about one slightly more complex. So the simplest one would be 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5. Now I know that this is a little bit subjective, but I was thinking about, okay, what's the second simplest function I could create on this set?
All of them. Just like
1 goes to 5, 2 goes to 4. 1 goes to 2.
1 goes to 2, goes to 3, goes to 4, goes to 5, goes to 1.
What?
Okay, not getting what I hoped I'd hear. What if we just swap 2 of them? What if I just said, instead of 1 going to 1, we'll say 1 goes to 2 and 2 goes to 1, and we'll leave the rest the same.
It's not very simple to think about.
Yeah, that is easy.
Right? That's about as simple as it gets. It's just swapping 2 elements.
Like 1 to 3 to 4 to 5 is easier.
Yeah, I agree.
So something like that, or maybe swapping these 2. Swap 3 and 4, or maybe we'll swap 3 and 5, so 3 goes to 5, 5 goes to 3. Maybe it's not the next simplest thing, maybe it is, but you'll agree, it's pretty simple. We'll just swap 2 elements. Okay, a permutation that just swaps 2 elements is what we mean by transposition. What's a transposition? It's a permutation that just swaps 2 elements.
Okay.
Now I'm telling you this because we're going to read this definition, and you're going to say, what? That seems like a real easy thing to say, but when you put it in rigorous writing, you find out it's kind of hard to say. What's a transposition? It's a thing that swaps 2 elements. It's a permutation that swaps 2 elements. Here's a transposition. Okay, let's read this exact definition now. Tau in S of n is called a transposition provided that there exists 2 numbers i and j in our initial set. So 2 numbers in here. In the case we have written here, i is going to be equal to 3, and j is going to be equal to 5 for this concrete example, because those are the 2 we switched. So I and j are the indexes we're switching. Okay. So it's a transposition if there exists 2 numbers I and j in your set, 1, 2, 3, all the way up to n. In our case up here was all the way up to 5. If there exists 2 numbers in that set, where those numbers are not the same number, so I and j have to be different numbers. We don't want to swap the same thing with itself.
Yep.
Such that the transposition maps I to j and the transposition maps j to I.
What?
The transposition, tau of I is equal to j, and tau of j is equal to I. The transposition maps I to j, and it maps j to I. I get so used to. Why am I writing my j backwards? And my I.
You're thinking of...
Yeah, I was confused about that too.
Sorry. Now I was erasing something, and I lost it.
Yeah,
That was weird. Alright. Weird moment there. J.
It's because of all this Greek writing that you're writing.
Yeah, the iota is throwing off my curvature, so now that J looks funky. Pick 2 different letters rather than I and J. Alright.
M and N.
Yeah, should have picked something like that. Can't use N because it's there. Should have done something like I and K.
P to Q.
Something.
Q is the worst letter.
Agreed that I and J were bad choices.
Okay.
Alright, so tau of I is equal to J. Look up here. Let's call this function right here tau. What's tau of 3?
5.
What's tau of 5?
3.
Tau of I is equal to J, and tau of J is equal to I.
Okay.
You follow that?
Yeah.
In other words, there has to be 2 elements that you swapped, and the rest of the elements have to not be swapped. That's what the second part's going to say.
Okay.
And for all k in the set, where k is not j and k is not
I.
for k is not I and k,
It's not J.
that was right.
Yeah,
What am I
that's
doing?
right.
Yeah. It's not then.
You're right, looks like a J.
I need to curve my eyes the other way. Okay. Jeez. For all k in the set, where k is not equal to I and k is not equal to j, k just maps to itself. So everything else maps to itself.
Mhm.
So I maps to j, and j maps to I, and everything else just maps to itself. Then it's a transposition.
Alright.
Pretty dense definition, but pretty simple when you understand what it's saying. Good?
Yep.
Yeah.
All right. So let's look at an example of a transposition. Here we have pi maps 1 to 1, 2 to 4, 3 to 3, 4 to 2, 5 to 5. Right?
Yes.
And it's a transposition. Let's write that out in cyclic notation.
1. 1.
In parentheses.
Yeah.
2.
2. 4. And parentheses.
And then all those by themselves.
3. And parentheses. 5.
You see how, except for the two elements I swapped, all the other elements are going to be paired by themselves.
Mhm.
I could have, if this were on S sub 100, then I would have had 6 by itself, 7 by itself, 8 by itself, 9 by itself, 100 by itself, right? That's really annoying. I don't want to have to write all this extra crap when I'm just writing a transposition, right? So now we have this shorthand for transpositions.
For the two letters that.
When it's a transposition, we just write it like this. We just write the one cycle we care about. All the other cycles just go to themselves.
How do you know it's a transposition, if that's all you see?
Because that's the
From
only-
here on out, this will be notation for a transposition. And I know that that's also notation for a point, that's notation for an ordered pair, that's notation for an open interval.
How do you know it goes to 5?
It will be, from context, we'll be talking about some set.
Okay,
And so you'll always know the set that it came from.
alright.
The same way that you'll know what identity is because of the set it came from.
So why do we care about transpositions? They seem so out there and random.
Because they're easy to write.
It's like breaking, kind of. The same way that for a big number, you have like its prime factorization. Well, now for a function, you can kind of have its representation as a composition of transpositions. You break it up into all its transpositions. Each transposition here, we'll get to it, but essentially, you're going to take some complex function and show that you can represent it as just a composition of a bunch of transpositions. It's like taking some big number and showing that you can represent it as a product of a bunch of prime numbers.
So can you do like a three-way transposition? 2 to 4 to 5. 2 to 4.
Transposition will always only swap two elements.
2.
It will only swap two elements. We're trying to say what's the simplest type of function that we could use to ultimately create, what's the simplest type of permutation we could use to ultimately create any permutation we want. And it's a transposition. You take a transposition, and by composing a bunch of transpositions together, I can ultimately create any permutation you want. So any permutation can ultimately be represented as a composition of a bunch of transpositions. Now I'm going to be saying that a lot, so don't get confused by those words. We're going to say composition of transpositions over and over again. Composition is combining functions. Transposition are simple functions. And each of those simple functions represents a single swap. Here's intuitively the way to think about it. If I've got the numbers 1, 2, 3, 4, 5, and I'm talking about different ways I can reorder them, I'm trying to create some reordering. I can ultimately create that reordering by swapping elements until I get what I want. Every transposition represents a swap. It's a functional way of swapping two elements. So if you were trying to give instructions to some kid, here's the order that the objects are in, and you want them to get it in the order 3, 2, 5, 1, 4, you might give them that order as a bunch of, listen, first swap these two, then swap these two, then swap these two, then swap these two, and you're done. That would be breaking this permutation, this whole permutation down into its component transpositions.
Okay.
So that's the use of a transposition. It's like breaking it down into just a swap.
How do you know what swaps go first?
Yeah, we'll figure out how to do that here in a second. You'll learn how to do that, and pretty much I think that's like all your homework problems are going to be is represent this function as a composition of transpositions. So that's exactly what we'll go over next. Gotta move my camera. Bit dense.
Pretty simple.
Pretty simple.
Yep. In fact, I think it's one of the, like, I've gotten this lesson more than I've gotten in any of the other lessons.
It's amazing what staying awake does.
I know.
Okay.
But I've been talking about it since the beginning of the year.
So am I.
When I was awake.
Well, that's good. Means you're getting smarter. Because this material is much harder than talking about things like proving an even plus an even is even.
That was hard.
It's hard for you.
Yes.
Okay.
But you won't get to evens and odds.
So let's get to some examples of how we can represent this now with transpositions. So here's some function, pi. Pi, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. Right? Now,
Yeah, the top one.
this one.
Alright.
All right. So now I'm going to show you one way that we can represent that as a composition of transpositions. Here's one way we could have represented pi. Here's the way the author does it. Now, what does he do? When you have it in cyclic notation, now we could have had pi could have been a bunch of cycles, right?
Mhm.
This is how you break down one of the cycles. So you do, here's what the author says to do. First you do these two as a transposition, then these two as the next transposition, then these two as the next transposition, then these two as the next transposition. That's the pattern here.
What are you trying to do?
Why doesn't it just start from the first?
When you compose all these together, it's going to ultimately reconstruct this function. So I'm showing you the pattern, and then we'll walk through how it reconstructed it.
Why
So you're
doesn't it
saying
just
that's
start?
how you undo it and undo it.
It's like I just barely did a prime factorization. I took some big number, and I said we can break this up into a bunch of smaller numbers multiplied together. I'm saying here's some big function that does a bunch of swapping, and we can break it up into a bunch of individual swaps.
That is there's no swapping. Yeah, that doesn't.
Yeah, it does. It
In
does.
this maps 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1.
That's
That's
cyclic
like 1, 1, 2,
notation.
2, 3, 3,
Look,
4,
let's
4.
write out that function exactly, up there. What is that?
1 goes to 2.
Right?
So what are you trying to do?
Hypothetical scenario. The books are in this order. You're talking to a toddler. You're trying to explain to them how to put the books in this order.
So right now.
Here's what you're going to tell the toddler. You're going to tell them, take the first and second book and swap in places. So they're going to start out here. Here's where they're trying to get. You with me?
Yeah, so they're gonna swap. So two.
So let's go
one,
through this
six.
process. Can you see on camera real quick? See if you can see my hand.
No, you can't.
No, you can
Yeah,
see,
you can see
see
it.
the hand, yeah.
You can see your hand,
Okay.
but like barely.
All right.
Can you see any of you?
Try and squish it into the space.
Yeah, you can see that.
All right. So we've got the objects in the order 1, 2, 3, 4, 5. We're trying to tell a kid how to get them in the order 2, 3, 4, 5, 1.
So just swap.
This to this is this permutation. Right?
Yeah.
Everyone with me so far?
Yep.
Now I'm saying going through this right here will ultimately do that. Each one of these we'll just intuitively think about it as a swap for now. We'll go through it rigorously and actually plug things into this function and we'll fill out what we get here. But let's just first think about it intuitively. I want you to think about a 1 and a 2 as swapping 1 and 2.
Okay, you just move.
You with
one
me?
into two.
So first we do this. So first swap the 1 and the 2. So now we have 2, 1, 3, 4, 5. Good?
Yep, now one.
Now I say swap the 1 and the 3. So now I have 2, 3, 1, 4, 5. Now I tell them swap the 1 and the 4. So now we have 2, 3, 4, 1, 5. Now I tell them swap the 1 and the 5. 2, 3, 4, 5, 1. And you're done. now you have this goes to this, which is what we wanted.
So that's just moving the 1.
So it's saying, how can I represent this permutation as just a bunch of individual swaps?
Starting from the identity.
Huh?
Starting from 1, 2, 3, 4, 5.
Starting from identity, sure. Yeah. That's the intuition for what these things are. Transposition we think about as a swap. Swap two things.
My question is, why didn't we start with 1, 5? Swapping 1 and 5. We would have got a different outcome, but it comes first. Which is my confusion.
Function composition, we always do right to left. You do this, then this, then this, then this.
Why?
It's
Not a
just,
convention.
we define g of f of x, when I plug x into this function, we define that to be g of f of x. You do the f of x first, then the g.
It's Japanese.
Oh. Wow, okay.
This is the way, I mean, you did stuff like this, like early in your algebra courses, right? Same thing,
I just
function composition.
never realized it was going from right to left.
Oh. Yeah, that's one of the annoying things to get when it comes to function composition is it's right to left and it often confuses you. But yes, that's the way it works. So yeah, you do this, then this, then this, then this.
And would it have given a different answer if you'd done it the other way? Started with 1, 5, then 1, 4.
Yeah.
Potentially. We already proved that last time. Composition is associative. It is not commutative.
Yeah.
Order matters on composition.
It would've
So
been fine.
potentially the same thing, but potentially a different thing.
That would have been good.
And here I think it would be it'd be pretty crazy if it happened to give the same thing.
It would be wrong,
That would be a crazy coincidence. That would be a crazy coincidence. All right. So now let's actually run it through and see this happen. All right. So we're going to plug 1 into this function and see what comes out. You with me?
Okay. Alright.
So when I plug 1 into this transposition, what comes out?
2.
2. So then we feed 2 into this. When I feed 2 into this, what comes out?
What? When you
3.
what comes out of 2?
No, I'm confused.
What do you mean?
This is a function.
Right.
Right? What does this function map 4 to?
It does not. 4 to 4.
It maps 4 to 4.
And that's 4 to 4.
Oh.
This function
Oh.
maps 1
Those are transpositions.
transpositions.
Oh.
Yes, I told you.
Okay.
Very confusing notation. You're going to lose track over and over again of what we're talking about. And that's going to happen over and over again. You're going to be like, oh yeah, that's a function. Yes, we're talking about functions and compositions. So this is a function. What does it map 3 to?
3.
3.
What does it map 4 to?
4.
What does it map 5 to?
5.
What does it map 6 to?
7.
There is a 6.
There isn't 6. 6 isn't so mean because it's a member of this set.
Okay.
Fantastic. We there?
Yep.
Okay, so when I plug 1 into this function, what comes out?
2.
2.
Now in composition, you take the output of this and plug it in as an input to this. Right?
Yes.
So 2 comes out of this and then we plug it into here.
You get 2.
When I plug 2 into this, what do I get?
3.
When I plug 2 into this, what do I get?
2.
2.
2.
Yeah.
Oh, right.
Right. This is a transposition. It maps 2 to 2.
Right.
All right, so now we still have 2. Now we pump 2 into this, what do we get?
2.
2.
And we pump 2 into this, what do we get?
2.
So ultimately, when we ran 1 through the whole thing, if we took this whole function, and when we plugged 1 into it, it was equal to
2.
2.
2. So this whole function, which is the same thing as pi, well, we're proving the same thing as pi, but it mapped 1 to 2.
Oh, I see.
Now we're going to plug into this function 2 and see what we get. When I plug 2 into here, what do I get?
2.
1.
You get 1.
2.
You get 1.
You get 2.
You get 1.
You get 1.
Because 1 and 2 are being
Right.
1
swapped.
and 2 and 2 and 1.
I don't know if those parentheses now are throwing you off. Here's a transposition. What does it map 2 to?
1.
1. This transposition maps 1 to 2, 2 to 1, 3 to 3, 4 to 4, 5 to 5.
Right.
That's it. So it maps 2 to
1.
1. This maps 1 to
3.
3. This maps 3 to
3.
3. This maps 3 to
3.
3. So when we fed 2 through this whole thing,
It's 3.
3 came out. Wonderful. All right, let's plug 3 in. What does this map 3 to?
3.
3. 1.
1.
1.
4.
4.
4.
4.
4.
3 goes to 4.
We're working on it.
Let's try again. Plug in 4. What do we get?
4.
4.
1.
5.
There we go.
5.
5.
1. Look at that.
And there we go. What did we get? We got 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, which is exactly what we were trying to get, this function right here.
Oh, cool.
This is going to be the type of homework problem you're going to have. You're going to be given a function like this and say, now, break it up into its transpositions. So you're going to be given this, and you're trying to come up with this. How did we come up with these transpositions? We did this and this here on the first one. And then this and this here. Then this and this here. Then this and this here. That's one way you can do it. Another way you can do it is you can just flat out start with 1, 2, 3, 4, 5. And you can just think to yourself, what do I want to swap?
1.
So you can be looking at this and just come up with it yourself. You say, I want to get 2 in the first spot. So first I'm going to swap 2 and 1. So 2, 1, 3, 4, 5, and just record what you did. If you swap 1 and 2 first, write that down. My first function is going to be 1, 2. First swap those. Now what do I want to swap?
3 and 1.
Well, I want the 5 right here, so maybe next I'll swap 4 and 5.
Yeah.
Just thinking about it to yourself. However you want to think about it.
Yeah.
So next I want to swap my 4 and my 5, right? So then I would do 2, 1,
Well,
3,
You should
5.
swap your 3 and your
4.
5, and then swap.
Well, I'm
your
just saying
5
I
and
wanted
one.
my 5 here, so I'm just going to swap it real quick. Doesn't matter what order we do this in. There isn't the right way to do it.
But you want your 4.
I'm just walking you through a random way to do it. So I swap my 5 and my 4, so that's my next one.
So that
Now swap your 4 and your 3, and then your 1 and your 3.
1 and your...
4 and your 3. Right now.
So next I'm going to, I'll swap my 1 and my 4.
Yeah.
So I'm going to do 2, 4, 3, 5,
That four's
1.
in the wrong spot.
So I did my 1 and my
3
4.
and 4, you can touch your 3.
You should have done 3 and 4 first.
Yeah.
Makes
And
more
now
sense.
I'm going to swap my 3 and my 4, and I get done in the exact same amount of steps.
So it's not faster.
No.
So no, you weren't seeing a shortcut. You were just seeing a different way to do it. 3 and 4.
Because your brain's different.
And there we go. So if I would have done this transposition, composed with this, composed with this, composed with this. Remember, writing right to left, I would have done 1, 2, 5, 4, 1, 4, 3, 4. And if I would have written out that transposition and we plugged it all in, it would have worked. Transpositions are just swaps. So there isn't the right way that you can do this. How many possible transpositions could I use to represent pi?
16.
What do you think the most is, roughly? Do you think it's going to be like 5 to the 5?
Oh, infinite.
Infinite? Why infinite?
You should always go back and forth.
Because you can always go back and forth. I can always have it as my next step, swap 3 and 4 again, and then swap them again.
Well, ignoring that.
Well, we're not ignoring that.
Well, without repeats, then it won't be infinite.
Without repeats, it won't be infinite,
I
but
don't know what it is.
allowing repeats, we could have done 2, 4, 3, 5, 1, and then I could have done 2, 3, 4, 5, 1 again.
And that's why people get B's in that.
And that's why people get B's in math, maybe.
Except for they already got the answer, so like 2, 3, 4, 5, 1 is the answer already. So you wouldn't be infinite.
But it's not obvious, because if we write these out as transpositions, well, maybe it is a little bit obvious in this exact case. But maybe you did an unnecessary swap somewhere along the ways. That's not obvious just from looking at the transpositions that you did an unnecessary swap.
You could just do
So while there's an infinite number of ways to do it, if you're doing redundant swaps, if you do a redundant swap, it's going to take another redundant swap to undo your redundant swap. Right?
Yeah.
So if the least number of transpositions I could have used to represent this function here was 1, 2, 3, 4, 5, then all its transpositions are going to be, they're going to be possibly 2 more, or 4 more, or 6 more, an even number more. Does that make sense? So I represented this thing as 5 transpositions. I could have also represented it as 7 transpositions, or as 9, or as 11, or as 13, or as 15.
So technically there's only 4.
Yeah, that first one doesn't count, does it?
The first one doesn't.
Oh, thank you. Good eye.
What if you just...
So we only used 4 transpositions to represent this function. So I could represent this function with 4 transpositions, or 6, or 8, or 10, or 12, or 14, or 16. If I can represent it as an even number of transpositions, it's impossible to represent it as an odd number. And if I can represent it as an odd number, it's impossible to represent it as an even number. We'll prove that here in a bit, but
That makes sense.
just jumping ahead, since I thought you're kind of seeing that right now. And it's because when you add one unnecessary transposition, you need another one to undo the one that you just did, intuitively. We'll have a much better way of thinking about it in terms of cycles, but let's keep going. Okay. So I told you that this is the way the author tells you to do it if you just want a formula for writing out these transpositions. That's not the way I do it. If you ask me to represent this as a bunch of transpositions, here's what I would have written. Still works. Here's the way that I think about it. I do those 2, then those 2, then those 2, then those 2, then those 2.
Good.
Okay, yeah.
So this would have been the way that I wrote it. Here's the way that the author would have written it if you asked him to break it up into the bunch of transpositions. And if you ran it through this way, you'd find out it still works. Same way. But if you're just looking for patterns, here's a pattern I like, here's a pattern the author liked. Make sense? Okay. And hopefully you know how to do that because that's going to be your homework.
But technically, you could go 4, 5, then 3, 4, then 2, 3, 4, 5, 6. And it still works the same. Oh, yeah.
You could have come over to the side here, just thought about it, and just recorded your work. It will work, yes. Now let's try this. This is what you do for each cycle. When you go to a new cycle, since it's just swapping elements in that cycle, it doesn't change anything. So let's really quick represent this now as a bunch of transpositions.
What is the...
Here is some big function. That's okay. A lot of new notation, easy to get confused. Here's some massive function in terms of in cyclic notation. Now I want to represent this big massive thing as a bunch of transpositions.
Okay.
You with me? Understand what I'm trying to do?
Yeah.
Okay, so here's what I'm going to do. You want me to use the author's method or my method?
Yours.
Mine. Okay, so I'm going to use mine. So first I'm going to write 1 and 2.
2, 3.
1 comma 2. Compose with 2, 3.
3, 4.
Compose with 3, 4. Compose with 4, 5. Those are going to be all those swaps. Compose with, now we just do this loop the exact same way. 6, 7. Compose with 7, 8. And notice that it doesn't matter if we have different loops, because nowhere over here were we ever swapping 6, 7, or 8. We were only messing with these elements. Right?
We just have to make sure we don't do 5, 6.
Right.
That makes sense. Okay.
And then, over here, 9, what does 9 go to?
9.
Yeah, 9 never got touched. We never swapped it with anything. So you have a single one by itself, you're not going to have it represented down here in a transposition anyway. And our last one is going to be 10, 11. 10, 11, 11, 10, doesn't matter, because you're swapping those two. Huh?
How'd you come up with that? Like what process
He's
is
a
that?
genius.
I don't know. You just see patterns.
So that's the pattern.
Yeah, that's the pattern.
Is that you just connect them with the next one that comes? That looks so easy.
Yeah.
So they're all-
But the author also had his pattern, right? He did those two, then those two, then those two, then those two. And you could have done it that way here. You could have done those two, then those two, then those two, then those two.
Then 6.
Then those two, then those two. Then those two.
Is that less than what you did?
Now, he's going to have 4 to represent this, 2 to represent this, 1 to represent this.
You
It's
have-
always going to be 1 less than the number in the cycle.
So with his method, it would just be 6 and 8 and 6 and 7.
His method, he would have had 1, 2, 1, 3, 1, 4, 1, 5, 6, 7, 6, 8, 10, 11.
That's not too bad.
No, they're both about the same.
Yours is better.
It's just a matter of, from here, it's just a matter of preference. But, so there's how you would represent it. And you can always check it. Do those swaps. See if you're understanding it right. Right?
But what is it supposed to be?
This is pi. Pi is equal to all those transpositions composed together. In other words,
So how would you check it?
To write it out.
you could run it through, or you could write out a table like we have here and just do those swaps. Write out all those swaps and see if when it's all said and done, you get 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, 6 goes to 7, 7 goes to 8, 8 goes to 6. This, when it's all said and done, better be the same thing as this thing right here. Right? Okay. Definitions now. We call a permutation even, provided that it can be expressed as an even number of transpositions composed together. And we call it odd, provided it can be expressed as an odd number of transpositions composed together. Question, is pi here even or odd?
Odd.
Odd, because 7 transpositions are what it takes to represent it. Is this pi even or odd?
Odd.
So even.
Even,
That's not.
because it takes 4 transpositions to represent it. Make sense?
Mhm.
Okay. Now, the sign of a permutation. The sign of a permutation we're going to call +1 if it's even, and we're going to call it -1 if it's odd. So if pi is this function right here, what's the sign of pi?
Oh,
Negative pi.
-1.
Negative 1, yeah.
If pi is odd, then its sign is -1. If pi is even, its sign is +1. So the sign of this permutation right here, is +1. The sign of this permutation is -1. Because when we represent it as a composition of transpositions, took an odd number.
So you just put negative pi.
What's the
Not
importance?
negative pi. Pi is a function. This maps a function to a number.
What's the importance of the sign? Like,
We're going to use that in some proofs here.
Okay.
Okay? So, should be a pretty simple definition. Here's the important thing I want you to know. If pi can be expressed as n transpositions, then its sign, the sign of pi, is always going to be -1 to the n. Let's make sure that makes sense. Let's pretend that pi was represented by an even number of transpositions. Right? Let's say 6. Let's pretend pi was represented by 6 transpositions. What's the sign of pi?
1.
+1, because it's even, right? What's -1 to 6?
1.
+1.
Cool.
You see that? Let's say that n were, let's say that pi was represented by 99 transpositions. What's the sign of pi?
Negative 1.
Negative.
-1. What's -1 to 99?
Negative 1.
Positive
Negative 1.
+1.
It's negative 1.
-1.
That's very sweet.
Anytime -1 is raised to an even number, it's 1. Anytime -1 is raised to an odd number, it's -1. You see why? Let's make sure we understand. If I write -1 times -1 times -1,
oh, right, okay, yeah.
now I believe you get it. Yeah, don't pretend you get it if you're still a little confused. If I write this out, then this pair together gives me,
Positive.
Or
it gives me 1. This pair together gives me
1.
1. If I have an even number, if I have 100 of these, which is an even number, how many pairs do I have? 50. Each pair is 1. What's 1 times 1 times 1 times 1 50 times?
1.
Just 1.
Right.
Right. So if we have an even number of if we have an even number of -1s, then that means that we can pair them all off. If we don't have an even number of pairs, then that means after we pair them all off, we're going to have an extra -1. So all these are going to turn into 1. We're going to have a -1. 1 -1 is just -1. Okay, make sure you understand that. Because we're going to be using this fact in our proofs here. Okay. So now, if pi and sigma are permutations, then the sign of sigma composed with pi, I think the author writes as pi composed with sigma. Doesn't matter. If pi and sigma are permutations, then the sign of pi composed with sigma is going to be equal to the sign of sigma, and I'll change the order here as well, because I think it's the order the author does, is going to be equal to the sign of pi times the sign of sigma.
Okay.
Not that the order matters.
No, we could switch the order here, and it won't matter.
Just
Because pi is just going to be, we're going to represent this as some number of transpositions. We're going to represent this as some number of transpositions, and when you compose those together, it's going to be the same number of transpositions regardless of what order they were in.
So sign an operation.
Sine is this function. It's going to spit out 1 or -1.
So it's like,
So this is going to spit out a 1 or a +1.
okay.
This is going to spit out a 1 or a -1 or +1. This is going to spit out a -1 or a +1. We're saying that the +1 or -1 that this spits out is going to be equal to the positive or -1 that this spits out times the positive or -1 that this spits out. We're going to prove that.
Is there an easy way to write how many transpositions a permutation has?
Turns out to be a really easy way to determine if it's going to be an even number or an odd number.
Well, can you write it like the cataract sign, whatever you call them, of a set to figure out how big the set is? Like, I don't know. That's not what it's like the absolute value difference.
Oh, cardinality.
Cardinality.
Okay.
I got C.
You did get the C.
Is there something like cardinality?
Couldn't you
Kind
just-
of.
couldn't
You
you
can
just-
talk about the smallest transposition, but it's not something we're particularly interested in. What we're interested in is it going to be an even number or an odd number
Could
of
you-
transpositions?
Can you just look at like if there were any numbers that were already in the spot they needed to go after you swapped everything?
We can even look at it simpler than that. So I'll show you a real simple way to think about it.
So I'm confused. If you had pi was equal to 5 and sigma.
Pi can't be equal to 5.
Well, that means it would be negative. There's 5
Oh, perfect. So pi has 5 transpositions, okay?
and then sigma's 3.
So 5 and 3 together has,
15.
that's a composition. This is I'm trying to make
it
this
says
clear.
that it's equal to the multiplication of them.
The multiplication
That's
of the
composition,
sign.
this is a multiply. So let's do what you were talking about, 5 and 3. This is 5 transpositions, this is 3 transpositions. Altogether, that's 8 transpositions.
And then
The
negative.
sign of 8 transpositions is positive 1.
Okay, yeah.
The sign of 5 transpositions is -1. The sign of 3 transpositions is -1. -1 times -1 is +1.
Valid.
Alright, we're going to prove that this always works.
Perfect.
So, let pi and sigma both be permutations, and assume that pi can be represented as x transpositions, and that sigma can be represented as y transpositions.
Okay.
Right? So x is either an even or odd number, we don't know. Y is either an even or odd number, we don't know. Okay, so then the sign of sigma composed with pi, I should have left the order the same, of pi composed with sigma, is going to be, what is it? The sign of your function is -1 to the number of compositions.
Transpositions.
Transpositions, thank you. So the sign of pi composed with sigma is going to be -1 to the number of transpositions
In pi.
in both their in the composition of both of them. This one had x of them, this one had y of them. Together we get x plus y of them.
Yep.
So that's equal to -1 to the x plus y. Now, adding in the exponents is the same as multiplying like terms. So that's the same as -1 to the x times -1 to the y. But -1 to the x is exactly what we mean by sine of pi, and -1 to the y is exactly what we mean by sine of sigma. Here's our proof. Pretty straightforward?
Yeah.
Yeah.
Cool. All right, next. Now, if pi and tau are both permutations, where tau is the transposition, then pi composed with tau has one more or one less cycles than pi did. What does this mean? So we've got pi, and it has some number of cycles in it. Like if pi is right here, then pi has 2 cycles in it. You with me? When I compose it with a transposition, we are always going to do one of 2 things. We're going to add a cycle or we're going to remove a cycle. Graphically. So when you think about this thing graphically, a transposition is either going to combine 2 cycles together or it's going to take a cycle and split it into 2 cycles. That's what transposition is going to do. Let me try to intuitively demonstrate this to you. So, we're not going to do a full proof of this, we're just going to get this one pictorially. So let's pretend that pi is some massive permutation that happens to have this cycle in it and this cycle in it. Maybe it has more cycles, maybe it doesn't, we're just going to focus on these 2 cycles. You with me?
Yeah.
So pi, whatever it is, it has this cycle and this cycle, maybe there's more, we don't care. Now I'm going to take pi, and I am going to compose it with this transposition, 4 and 7.
Okay.
Now, since 4 happens to be in one cycle, and 7 happens to be in another cycle, composing it with this transposition is ultimately going to hook these 2 cycles together. So that's what happens. When I take my permutation, and I do a transposition where the 2 terms in the transposition come from different cycles, it's going to merge those 2 cycles together. If the 2 terms came from the same cycle, then that, turns out, splits the cycle at those 2 terms.
Got it. That makes sense.
That's pictorially what it does. Let's go through a concrete example so you can see it all in action. Okay, so here's pi. 1, 2, 3, 4. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5. That's right here. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. And then 6 goes to 7, 7 goes to 8, 8 goes to 9, 9 goes to 6. That cycle's right here. And then maybe it had other cycles. We don't care for this picture. With me so far?
Yeah.
Now, let's compose it with 4. Let's do the transposition with 4 and 7.
Okay.
Now, notice that putting 4, 7 here, it doesn't change what 1 goes to.
True.
It doesn't change what 2 goes to. It doesn't change what 3 goes to. It doesn't change what 5 goes to, or 6 goes to, or 8 goes to, or 9 goes to. They'll still all go to the same thing. It's only going to change what 4 and 7 goes to, right?
Yeah.
What 3 and 6 goes?
No. When I plug 3 into this, what does it go to? This transposition maps 3 to
3.
3. And then we plug it into pi, and pi maps 3 to 4 same way it always did.
Okay.
Right? When we plug 4 into this, what do we get?
7.
7. When we plug 7 into this, what do we get?
4.
8.
8.
Oh.
So now, when we do all of this, 4 no longer maps to 5. 4 now maps to
8.
8.
Oh.
It now maps to whatever 7 used to map to.
Got it.
So 4 no longer maps to 5. 4 now maps to 8. You see that?
Yep, and 7 now maps.
4 now maps to whatever 7 used to map to.
7 maps.
And 7 is going to map to whatever 4 used to map to. So run 7 through here, what do we get?
5.
4.
When I run 7 through here, what do I get?
4.
4. Run 4 through here, what do I get?
5.
So now, in the whole thing, 7 now goes to 5. So now 7 goes to what 4 used to go to. So 4 points to what 7 used to point to. And 7 points to what 4 used to point to. That's what the transposition does graphically. And so we just barely combine these 2 loops into one loop. Make sense?
Yeah. Which is.
Which is the picture that we have down here, just written all out. 1 goes to 2, goes to 3, goes to 4, goes to 8, goes to 9, goes to 6, goes to 7, goes to 5, goes to 1. I just rewrote this exactly. With me? So I'm going to restore this picture to how it was. But you see now how, when we take these 2 loops and apply this transposition, it gives us this loop, right?
Yeah.
We're going to call this loop down here, whatever function we have when it's all said and done, we're going to call sigma. So now let's see what happens with sigma, and sigma could have some other loop somewhere else, who cares? We're just going to focus on this loop. Now let's see what happens when you have something like sigma, and you apply transposition to just one loop. Then what happens? So now notice down here, when I apply the transposition 4 and 7 are now in the same loop. And so now it's going to break the loop. Pictorially, what's going to happen?
It's just gonna
4 is now going to go to whatever 7 used to go to, right? So 4 is now going to go to 7, what 7 used to go to. And 7's now going to go to what 4 used to go to. And so it's going to break it into these two cycles. And redrawing those two cycles up here are these exact cycles. So when you apply a transposition, you're either doing one of two things. You're combining two cycles together. If both the terms are in different cycles, you're combining two cycles together. Or if both the terms are in the same cycle, you're splitting the same cycle into two. You with me?
Yeah.
So if I know that this function here has 10 cycles, and I apply a transposition to it, how many cycles do I have now?
9.
I either have 9 or I have 11.
Yeah.
Yeah.
So now you know that.
I either created a new cycle or I combined two cycles together.
So now you know what sign is -1.
Maybe. Oh, did I tell you how many loops? Yeah.
And you said.
Okay. But the point is, when we apply a transposition, we either add a cycle or we remove a cycle. That's graphically what a transposition does.
Alright.
Okay? So now, let's
We're going to go over that.
What about like your note with plus and minus 1? Very bottom.
Bottom of what you're just doing.
Oh, shoot. Yeah. Right up here. So now we're going to have another notation. So if I know that pi is in S sub n, then C of pi is equal to the number of cycles. So over there, when pi had 2 cycles, C of pi is 2. So looking at the example, the picture we had over there, C of pi was equal to 2, and C of sigma was equal to 1.
Right.
So that was that note. And then I said, notice this fact, that C of pi composed with a transposition is going to equal C of pi plus or minus 1. Because composing with a transposition either added or removed a cycle.
Yeah.
So that's what that second note is. You good? That marker's kind of crap. Over here, realize this as I was walking home. Don't read all those things. That's a dead marker. That's a dead marker. Seems stuck with a crappy one. And I tricked myself and did not grab the non-dead one. Okay, non-dead marker. Talked about that, no, okay. So, we already talked about this, but let's go over it again. How many ways could we represent pi equal to this function as a composition of transpositions?
Infinite.
An infinite number. There isn't a right number of ways. But what we did talk about earlier is if we can represent it as an even number of transpositions, then any new way we represent it as a number of transpositions, it will still be even. Like if we could represent it as 6, then we could represent it as 8 and 10 and 12 and 14. Because we could add a transposition that we didn't need and then undo it.
Okay.
Similarly, if I could represent it as 5 transpositions, then I could also represent it as 7, as 9, as 11, as 13. You with me?
Okay.
So what we're going to try and prove is that if pi is a permutation, and it can be represented as this many A transpositions, and it can also be represented as B different transpositions, then A and B have to have the same parity. They either, A and B both have to be even or they both have to be odd. In other words, if I can represent pi as 10 transpositions, it is impossible for me to also represent it as 11 different transpositions. I can do 12, but not 11. If this is an even number, then this has to also be an even number. I can't do an even and an odd. If this is odd, this has to be odd. If this is even, this has to be even. Can't do both. That's what we're ultimately going to prove. Okay. This is going to imply this, but let's make sure that we understand this. So we're not actually going to prove this directly. We're going to prove something a little bit more useful, but this gives us this for free. It's just says it in a slightly more complex way. So if pi is a permutation, where pi can be represented as A transpositions, then A is always going to be equivalent to some number mod 2. Forget this for a second. What is this number? Who cares? Drop that for a second. The number of transpositions is always going to be equivalent to this mod 2. When are two numbers equivalent mod 2? When they're both even or they're both odd. You with me?
Yep.
So what am I saying? I'm saying anytime you can represent pi as some number of transpositions, that had to have the same parity as whatever this number is. If this number is even, A has to be even. If this number is odd, A has to be odd. So let's pretend for a second that this number, I know you don't know what this number is, we'll figure it out here in a second. But let's pretend that this number is 8. Then that means the number of transpositions I can use to represent pi will always be an even number. It will be impossible for me to use 13 transpositions to represent pi. You cannot do 13 swaps and end up with the arrangement I told you to come up with. Does that make sense? Okay. Now what is this number? N here is the same n that we were talking about in here. If pi came from S sub 10, then this n here is 10.
Alright.
And what is this number? This is the number of cycles.
How do we find that?
The number of cycles,
If we don't give it being
when you have it in cyclic notation, it's pretty obvious. When we have, so if we're looking over here at, let me just rewrite one over here, pi, but we could have pi is equal to 1 goes to 2, goes to 3, goes to 4, 5 goes to 6, 7 goes to 9, 8 by itself. Okay, what is n? N is 9. This is using 9 elements. So in this case, our n is equal to 9. What is our number of cycles?
5, 4.
1, 2, 3, 4 cycles. What is 9 minus 4? 5. 5 is an odd number. Any way you represent this as a composition of transpositions, it will always take an odd number of transpositions to represent it. It's impossible to do an even number. That's what we're going to prove.
Okay, that makes sense.
All right. So make sure you understand this number.
What is A?
A is the number of transpositions here.
Okay.
So the number of transpositions you use to represent the function will always have the same parity as n minus the number of cycles in pi.
Okay,
Okay.
that makes sense.
Make sense? What we're trying to prove? All right, let's write this out. So first off, let pi be something in S of n, some permutation, such that it can be represented as a composition of A transpositions. Now we're going to consider a sequence. And we're going to, it's like the steps that you take. Remember when I wrote over in a column? I wrote over in a column over there. We start out with 1, 2, 3, 4, 5, and we do one swap at a time.
Yes.
So we start with identity and we do one swap at a time. That's exactly what we're listing out here. Start with identity, then do the first transposition. Then once you did the first transposition, now do the second and first transposition together. Now do the first, second, and third transposition all together. dot, 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 all the way out until we do all the transpositions. So we're just looking at the sequence.
Alright.
You with me? So the sequence we have written right here. So you start with identity, then look at just the first transposition by itself, then look at just the first and second transpositions by themselves, then the first, second, and third transpositions by themselves, all the way down until we're looking at all the transpositions. When we have all the transpositions, this is the same thing as pi. Don't forget that this is pi right here. Pi is equal to that thing. Right? Okay. Now, first off, starting with the identity function. How many loops are in the identity function? How many cycles are in the identity function?
As many as there are.
If it has n elements, let's assume that we know what n is.
So there's n.
How many loops are in identity? N loops, n cycles, because it just maps everything to itself. So if you have n elements, you're mapping all of them to themselves, you have n loops.
Okay.
So what is n minus the number of loops?
0.
0. So for identity, n minus the number of loops is always 0.
Yeah.
So if you're ever trying to represent identity using transpositions, it's always going to be an even number of transpositions. Make sense?
Yep.
Because you can represent it as do a swap, then put it back. You're back where you started, right? Okay, so then our first transposition that we do, how many cycles does it have? How many cycles do we have after our first transposition?
We have 4.
One less
So we
word.
start out with graphically,
N
let's
minus
say,
1.
perfect. So let's pretend we had 1, 2, 3, 4, 5. Here's what we have, and we have them all looping on themselves. Identity, right?
Yeah.
Now what does a transposition do?
Connects to.
It's going to have to connect two of these together. That's the only thing we can do.
Because they're all separate.
Right. So now it's going to connect these two together. It's going to have 3 goes to 2 and 2 goes to 3. Right? So we're going to have one less loop than we started with. So identity had n cycles. Once we apply the transposition, we're going to lose one of those cycles. So we have n minus 1 cycles. So n minus 1 is equal to what?
1.
1. Hopefully no one's getting confused on the algebra there. N minus 1
I confuse myself.
is equal to 1. Right?
Is it
Yeah.
negative 1?
That makes sense.
Now, if we do 8 minus 7, we get 1.
Oh, that's right. I lost myself in the algebra.
8 minus 1 less than 8 gives you 1. Or the algebra.
How?
Apply the negative to both terms. When you distribute the negative, that becomes minus n and plus 1 is equal to 1.
Got it.
Isn't-
However it makes it click.
Oh. Yeah.
Oh,
Okay.
Okay, we click it.
Yes.
Alright.
You guys really need some algebra.
Yeah.
Seems like a bunch of people who started but didn't finish the algebra course I did.
Huh.
Huh. Probably would have been useful.
I was there and I was so confused.
I'm feeling targeted right now.
Good. I'm trying to target all of you. Except for you, I think you stuck with it.
I stayed there the entire time.
You did?
College algebra.
I don't
I
think you
missed a
did.
couple classes, but
What
I
was
stayed
it?
there.
Oh,
there was a couple.
Huh?
What was
Okay.
it called again? Advanced
College
algebra?
algebra.
This is just college algebra.
I think this is when I broke my leg, so I just didn't want to go anywhere.
Oh, I think you're right. Anyways,
That's
All right.
hilarious.
so when we apply one transposition, n minus our number of cycles is for sure going to be 1.
Yeah.
True.
Right?
Yeah.
That's what we were hopefully figuring out there? Okay. Now if I add another transposition, what did I do? I either added another cycle by breaking the cycle we just created.
Or you made or you subtracted a cycle by adding two
Right.
together.
So I either broke a cycle into 2, so added a cycle, or I combined 2 cycles into 1, removing a cycle. So we either added 1 or we subtracted 1.
Okay, that's right. And part 3 is wrong.
Wait.
And
wait,
so if
hang
I,
on.
what?
Part 3 does not look right, but you can get to that.
Wait, what if you connected 1 to 2 and 3 to 1?
Look, we're looking at this. I apply transposition. I now have 2 options. I can either combine those 2 together to make a new loop,
We'll break it there.
or break the loop we just created.
So you can't do like make so that 1 is connected to 2 and 3.
Oh, sure. I can connect this into this loop,
Yeah.
which gets rid of one loop.
Oh.
So I can either combine two loops together, getting rid of a loop, or I can break an existing loop.
Okay.
Right?
Yeah.
And so, if I added a loop, then this number gets one smaller. If I subtracted a loop, then this number gets one bigger. Either way, we plus or minus 1 to this number. If I plus or minus 1 to the loops, I plus or minus 1 to whatever number we have here. Right?
Yeah.
Right?
And if I add another transposition after that, I either plus or minus 1 to loop, so I plus or minus 1 to this number down here.
What if you have 1 and you minus 1 and you minus 1 again?
Well, you could start saying there's restrictions that, okay, those both can't be minus 1. But we won't even have to care about that detail, it turns out.
Okay. Why?
You're right, that it doesn't make sense for it ever to be negative.
Yeah.
And we can note that, okay, it can't be negative. But it turns out we're not going to care. Because all we're ultimately going to care about is this even or odd.
Right?
Okay, anyway, so we keep listing this out. So by the time we listed it out for pi, so when we get to pi, which is all the transpositions, then the number here is going to be 1 plus or minus 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 1 a times. For each transposition, we added a 1.
Yep.
So by the time we get back all a transpositions here, we're going to have 1 plus or minus 1 plus or minus 1 a times. Now, let's notice this really quick. 1 plus or minus 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 1. We can keep going as long as we want until you get the pattern, but I think you'll get it really quick. We start with 1. Is 1 even or odd?
It's odd.
It's odd. So I'm going to put an O for odd. Now, if I take 1 and I add 1, is it even or odd?
Even.
If I subtract 1, is it even or odd?
It's even.
It's even. Either way. So either way, when we plus or minus 1 from an odd, we get even.
Yep.
Once again, if I have an even and I plus or minus a 1,
It goes odd.
it's going to be an odd. Then if I plus or minus 1, it's going to be even. Plus or minus 1, odd, even. So if I had an even number of 1s that we plus or minus together, the total sum is going to end up even. If instead we had an odd number of 1s that we plus or minus together, the total sum is ultimately going to be odd. Everyone see that? So, remember, a is the number of 1s we have here. So if a is even, then all these 1s, when we add them up, it's going to be a
Even number.
even number. And if a is odd, then when we add up all these 1s, it's going to be a
Odd.
odd number. Has everyone seen this?
Yeah.
You got it? Okay. So, observe that n minus the number of cycles, which is equal to 0 plus or minus 1 plus or minus 1 plus or minus 1 a times. We can forget the 0 plus or minus there. Could just write it like this. 1 plus or minus 1 plus or minus 1 a times is going to be even if a is even, and it's going to be odd if a is odd. So we just really said that this number right here is even when a is even, and this number right here is odd when a is odd.
That doesn't
Therefore-
make sense. Wouldn't it be true or false, not odd or even? Not how that one works.
Well, we did an earlier proof that a is congruent, that two numbers are congruent mod 2 if and only if they have the same parity. That's an earlier proof from the class. So we can use that fact. So we just barely showed that this number always has the same parity as a. Therefore, a is congruent to that number mod 2. Make sense?
Yep.
And then a quick corollary that we get for free. Then the sign of pi is always just -1 to the n minus the number of cycles.
Oh, yeah.
Okay.
So you can quickly figure out the sign of a permutation just by looking at it. See what n is, see what the number of cycles is, then raise it to that power, and you instantly know its sign. Plus or minus 1.
Yep.
Good? Okay, that's the end of that. So there's permutations. Get started on your homework. Test next week. Don't forget, homework solutions are already posted online on the Facebook site. Any other questions before we turn off the recording?
I have questions about past lessons.
About past lessons? Okay, yeah, we don't really record that. All right, we'll call it there.